Welcome to our SMI OCP 2020 Tech Talk. My name is Gary Adams. I am the Director of Enterprise Marketing for Strategic and Business Development. Title today for our presentation is Silicon Motion's SSD Controller Focus on Data Center and Storage Trends. Let's talk a little bit about SMI before we get started. Since 2009, Silicon Motion has shipped over 6 billion NAND controllers into the market. From our first shipment of compact flash controllers, SMI has continued to provide innovative products for SD cards, USB flash drives, and embedded memory controllers. Some of the key market-leading products today that we're shipping continue with NAND controllers for client and enterprise SSDs, as well as our single chip SSDs. If we discuss SMI's role and market position, SMI has a strategic relationship with NAND manufacturers as either a direct supplier or a collaboration partner for NAND enablement. We partner with storage module makers or direct customers, enabling our products across all markets ranging from mobile, automotive, consumer, client, and enterprise. It is likely today that you will have a digital experience with data that was touched by an SMI NAND controller. Silicon Motion is focused on providing a comprehensive product portfolio for enterprise storage and data center. We offer vertical integration and innovation ranging from our NAND controllers backed by our turnkey firmware and reference designs, our applications optimized SSDs, our all-flash arrays, as well as our software-defined storage solutions. SMI is the partner of choice when selecting storage solutions focused on performance, reliability, and security while reducing your total cost of ownership. If we look at Silicon Motion's go-to-market in assistance with its customers, we can provide a turnkey reference design. This includes the NAND controller ASIC, the firmware reference design kit, as well as firmware optimized for that platform. We also have a model where we provide the ASIC controller and just a software development kit with reference design code that enables our customers to do their own firmware development. We also have a model of firmware customizations to customer spec, as well as a complete custom engagement for both ASIC and firmware that are designed to customer spec. If we look for our particular discussion today, what we'd like to share in a few slides is Silicon Motion is focused that aligns to data center and storage trends. Areas of discussion will be our form factor modernization, application optimized SSDs, as well as future controller considerations. Let's start with form factor optimizations. We're all familiar with the enterprise and data center SSD form factors, EDSFF. Highlights of the EDSFF collaboration include a common connector spec and pinout that accommodates by 4, by 8, and by 16 connectivity. It has done future proofing for PCI Express Gen 3 and through Gen 5. It optimizes increasing capacities while providing operational efficiencies at higher power envelopes, with the ultimate goal to reduce the need for proliferation of additional form factors. While we believe that the many current form factors, for example, U.2 or U.3 as well, will have long life, including M.2, especially for boot drives, we're excited to see the adoption of many data center customers to adopt E1.S for 1U servers. If we look and take a moment and look at E1.S specifically and compare it to M.2, we look at really 3 areas where it's very notable that we see striking benefits. One is that E1.S is hot pluggable, allowing for improved serviceability. We see the ability for increased capacity support. For example, in M.2, we see most suppliers providing 4 to 6 placements of media, while on the E1.S, we can get 10 to 12 placements, depending on the manufacturer. The E1.S standard also allows for a number of different types, which accounts for symmetric and asymmetric enclosures, as well as heat spreaders up to a height of 25 millimeters. This flexibility of carrier cards and heat spreaders allows for better thermal optimization and reduced EMI and reduced ESD issues. If we talk what SMI is doing with EDSFF, last year we launched our new Gen 4 8-channel project targeting data center. We chose the E1.S for our reference design kit to enable customers' SSD designs, with the picture that's shown on our slide here. What we did is our initial floor planning, we're considering looking at using DRAM, the power loss protection circuitry, as well as the controller footprint, additional design elements. We could comfortably put NAND placements on board. We also looked at maximizing the bandwidth and performance that was achievable while keeping a NAND transfer rate at about 1200 mega transfers on each of the 8 channels of the design. With performance modeling that including considering trace links loading effects, we could comfortably support 4 CEs per channel on 8 channels across all 10 placements. So the conclusion for our initial SSD configurations with the existing NAND technologies that we'd support user capacities up to 8 terabytes for both read-intensive and mixed workload applications when considering different levels of over-provisioning. Up next, we'll be modeling heatsink efficiencies up to that 25 millimeter height fin while maximizing for performance in QoS, and we'll be showing our progress at FMS. Now we can start talking about application SSDs. It has been well established that SSD users that have application awareness can give significant system level optimizations by directly managing data placement within the NAND. Let's look at a couple of examples. Open Channel is a framework that provides an SSD architecture based on an NVMe protocol describing a media interface between the host and the SSD. It enables partitioning of functions and data placement. The main function FTL can be executed from the host side while managing functions like NAND access and error correction are implemented in the SSD device itself. There's well-known benefits for using Open Channel, which includes application I/O isolation, which improves garbage collection, as well as write amplification. Your endurance extension that you can provide to the NAND, as well as the ability to do independent I/O scheduling, lowering effective low latency and improved QoS. We can also remove redundant mapping, which improves overall media utilization. SMI has a history of supporting the Open Channel SSD 0.8, 1.2, as well as the most recent Denali version 1 spec in its Open Channel SSDs. We will continue to collaborate with customers on our Open Channel SSD developments. If we move on to key value store, Silicon Motion provides key value store SSDs today that's an extension of our existing Open Channel infrastructure. Traditional KV applications that use unstructured data like RocksDB, MySQL, or Ceph suffer significant bottlenecks when attempting to access traditional block-based storage devices. With KV-specific media interface and collaboration drivers, we can see dynamic system-level reduction and write amplification and improvement in system-level data writes. Key value SSD benefits includes linear scaling of storage performance, inclusion of metadata, the improved resource utilization, lowering system cost, as well as I/O efficiencies that remove bottlenecks in a processing path. SMI continues to collaborate with customers on KV SSD developments and has a number of roadmap items in this space. There's been a significant amount of effort in extending to create standards around common applications that take advantage of host awareness. With the introduction of namespace types, industry momentum supporting ZNS, which has taken many of the latest concepts to open channel, and KV, as well as computational storage, can now be looked at from a standards perspective and leverage the NVMe standard benefits that we see, which includes early adoption and qualification by maintaining abstraction and appearance of hard disk drives from the system users. There's no need for a host understanding of the underlying firmware and control of the FTL and media management within the SSD. We have common methodology to define functionality and performance within the SSD, as well as a robust ecosystem to drive commodities of scale. Silicon Motion supports applications optimized SSDs in both the NVMe standard as well as unique customer engagements that are existing today. Lastly, let's discuss the use of modern controller architectures and what SMI is doing in this space. When we step back and we look at controller architectures, we want to look at isolation for a moment. Isolation can be broken down into many areas, which includes just the logical with no physical isolation. Examples we see here is in the SROV standard supporting virtual functions. We have the concept of physical isolation within the controller, and how would we do that? Would we do it statically or dynamically within the design? Would we, when we look at media isolation, examples would be through NVMe sets or endurance groups, or timing isolation that we do in the design with the predictable latency modes. You kind of think of the related IOD specifications. We also have the opportunity to decompose controller resources for isolation. We look at queues, buffers, accelerators, processor cores, and the priority settings around these, as well as functional elements that you see for isolation, like firmware in FTL or garbage collection, and as well as management functions. The challenge here is that these are all very complex topics, and as we look at controller designs, we need to step back and look at both hardware and firmware design, and how is it used from an entire SSD design from beginning to end. We'll be looking as well as performance and throughput balancing and managing QS with and without isolation. And just one specific example of this is how do we manage open blocks with different features that are being used within standards today. So there's lots of complex work that needs to be done. And let's share what we've been doing with over a couple of slides. So today we have in volume production our SM2270. What we've done in the SM2270 architecture is we've sliced our 16-channel controller into two logical back-end slices that use 8-channel each. In those back-ends, we have separation. They're the physical back-ends with XOR, CPU, DRAM, and NAND channel resources that work independently of one back-end to the other. In production, we use this architecture in the open channel environment, optimizing data placement and reducing noisy neighbor effects you would see, and have seen very good results when comparing against using shared resources across 16 channels. This year, we'll continue this investigation for the architecture optimizations by using NVMe sets in a standard firmware stack environment and continuing to identify improvement areas. As we look at next generation, we'll continue to use our slice concept in the architecture. Our next generation 8-channel device will be trying to provide four 2-channel SSDs physically isolating those back-end resources that we previously discussed, as well as bringing on, from a standard firmware stack perspective, the support for NVMe sets with IOD, and comparing those data results with ZNS. So if we were to now wrap up and provide a summary of our discussion points today from what SMI, and the takeaways we'd like you to look at is SMI provides a comprehensive product portfolio focused on enterprise storage and data center. We're your collaboration and partner in exploring storage performance and application across application optimized SSDs. We continue to invest in innovative architectures for maximizing performance at scale. We're an active participant in standards to accelerate time to market for seamless qualification, lowering your total development cost, as well as we're looking forward to working with our OCP partners and customers in creating innovative storage solutions. We want to welcome you to visit us at the Silicon Motion virtual booth, where we have a comprehensive portfolio of products focused on enterprise and data center. Thank you.